When membrane technology first hit the scene in the water industry, it was a game changer. Now, membranes are a ubiquitous part of the treatment process for water and wastewater systems of all shapes and sizes. But what's next for membranes? Hello everyone, I am Sheena May De Leon and I will be discussing the advances in membrane technology research for water and wastewater treatment, its advantages and disadvantages, and its future directions and challenges. The presentation's content outline is provided in front of you. We will begin with the problem statement, followed by the solution and an introduction to membrane technology. Then we'll talk about its current trends and advancements in water and wastewater treatment. Following that, we will define its future directions and challenges. Then we'll wrap it up with a brief conclusion of the topic. So let's begin. All activities of mankind are water dependent. With the increase in human population, tons and tons of wastewater are produced every day across the domestic, industrial, and agricultural sectors. Freshwater resources, however, do not get replenished to accommodate the ever increasing population and its water usage needs. This has led to intense competition and unfair distribution of the limited freshwater resources among the various sectors. Consequently, many people around the world, especially in developing countries, lack access to potable water. Evidence of these situations is seen across the world, especially in the Middle East, Africa, Asia, and Latin America. With efficient wastewater treatment, freshwater resources can be supplemented and potable water can be made accessible to all. This seems to be the most obvious way of dealing with water scarcity. In this vein, several efforts have been made over the years to introduce various wastewater treatment technologies, such as conventional filtration, coagulation flocculation, and biological treatment systems, among others. There is also improvement of already existing technologies to meet current discharge or reuse standards. One of the wastewater treatment technologies that have seen a major boost over this period is membrane technology. Membrane technology has grown significantly in the last couple of decades due to the benefits it offers in water and wastewater treatment. Basically, a membrane is a barrier which separates two phases from each other by restricting movement of components through it in a selective style. Membranes have been in existence since the 18th century. Since then, a lot of improvements have taken place to make membranes better suited for many different applications. A wider scope of industrial and environmental applications of membrane technology are based on its advantages, such as clean technology, energy saving in most cases, ability to replace conventional processes such as filtration, distillation, ion exchange, and chemical treatment systems. A schematic representation of the applications of membrane technology is depicted in the figure. Other advantages are its ability to produce high quality products and its flexibility in system design. Because of its multidisciplinary application, this technique is applied in several industries, including water treatment for domestic and industrial water supply, chemical, pharmaceutical, biotechnological, beverages, food, metallurgy, and various separation processes. Moreover, the drawbacks associated with membrane technology include two major phenomena, that is, membrane fouling and membrane modules, which we will be dealing with briefly in the latter part of the presentation. Characteristically, membranes can be classified as isotropic and anisotropic. Isotropic membranes are uniform in composition and physical structure. They can be microporous, or which in case their permeation fluxes are relatively high compared to when they are non-porous or dense, where their application is highly limited due to low permeation fluxes. Isotropic microporous membranes are widely applied in microfiltration membranes. And isotropic membranes, on the other hand, are non uniform over the membrane area and are made up of different layers with different structures and composition. These membranes have a thin selective layer supported by a thicker and highly permeable layer. They are particularly applied in reverse osmosis processes. In terms of membrane material makeup, membranes are classified as either organic or inorganic. Organic membranes are made from synthetic organic polymers. Mostly, membranes for pressure driven separation processes such as microfiltration, ultrafiltration, nanofiltration, and reverse osmosis are made from synthetic organic polymers. These include polyethylene, polypropylene, and cellulose acetate, among others. Inorganic membranes are made from such materials as ceramics, metals, zeolites, or silica. They are chemically and thermally stable and used widely in industrial applications like hydrogen separation, ultrafiltration, and microfiltration. The movement of media through the membranes is based on different driving forces. There are equilibrium based membrane processes, non equilibrium based membrane processes, pressure driven, and non pressure driven processes. The schematic diagram on the slide shows a summary of some of these techniques according to their driving forces. These membrane techniques will be discussed throughout the presentation. Now, let's start with pressure driven membrane processes. Pressure driven membrane processes are by far the most widely applied membrane processes in wastewater treatment, from pretreatment to post treatment of wastewater. These processes rely on hydraulic pressure to achieve separation. There are four main types of these processes. These are microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. The main difference exhibited by these processes, apart from their pressure requirements, is their membrane pore sizes. The table on the next slide provides a summary of the main features of these processes. Among the pressure driven membrane processes, the reverse osmosis is highly known for its efficiency in separating small particles, including bacteria and monovalent ions like sodium ions and chloride ions, up to 99.5%. The reverse osmosis has been at the forefront of water reclamation through wastewater treatment and desalination of seawater for a long time. During reverse osmosis, a hydrostatic pressure is generated that is strong enough to overcome the intrinsic osmotic pressure of the feed. This is against the natural osmosis process. For the complete process, the water molecules are absorbed into the membrane surface under pressure. These molecules diffuse through the membrane material and finally desorb at the permeate side of the membrane for collection. Different combinations of these pressure driven membrane processes have been applied in different wastewater treatment settings. In some cases, they serve as pretreatment to other unit processes. In an experiment, Nataraj et al. Combined the nanofiltration and reverse osmosis to treat distillery wastewater in which an average of 98% of contaminants, the color, total dissolved solids, chemical oxygen demand, and potassium, were removed successfully. In another application, ultrafiltration and reverse osmosis were combined in a pilot scale plant to treat wastewater from reactive dye printing. After the ultrafiltration, the permeate still fell short of the discharge limits. However, the reverse osmosis permeate was fit for discharge and reuse. Contaminants such as urea, sodium alginate, reactive dye, and oxidizing agents were successfully removed. Several other instances of applying these pressure driven membrane processes are shown in the table. As seen in the most of applications listed above, the microfiltration, ultrafiltration, and nanofiltration usually serve as pre-treatment steps to reverse osmosis. This is to reduce fouling of the reverse osmosis membrane and to enhance the maintenance of constant flux. This also serves as a multi-barrier treatment for removal of contaminants from wastewater. The pressure driven membrane processes have undoubtedly made water reclamation from wastewater a good option. However, the challenge still remains with the energy requirements due to the pressure. Forward osmosis. As shown in the figure, the forward osmosis follows the natural osmosis process where water molecules are drawn from one solution to another through a semi permeable membrane. In this case, a draw solution, which is highly concentrated, is used to provide a concentration gradient to draw water molecules from the feed solution. This gradient provides the needed osmotic pressure difference to drive water molecules from the feed solution to the draw solution. This movement continues till an equilibrium of chemical potential is reached, unless for niche applications where the water being drawn from the feed forms part of the product, there is always the need for a recovery unit. This unit simultaneously recovers fresh water and regenerates this draw solution. The forward osmosis has been applied for the treatment and concentration of different streams of wastewater. Holloway and others applied the forward osmosis in concentrating anaerobic digester concentrate, in which a reverse osmotic system was used to recover and reconstitute the draw solution. Similarly, York and others applied the forward osmosis in a landfill leachate management using sodium chloride as a draw solute and reverse osmosis to recover and reconstitute the draw solution. Up to 95% of the permeate was recovered. In other applications, Zhang et al. Combined the forward osmosis and membrane distillation to recover water from oily wastewater. Hout and Lurch conducted a series of forward osmosis experiments to investigate the applicability of forward osmosis in an automobile production site and dairy industry. It was found out that cathodic dip painting, rinsing water, and paint shop pretreatment wastewater proved well as feed solution when 1 molecule per liter of sodium chloride was used as draw solution and can therefore be utilized in an automobile production site in wastewater treatment. Thus, forward osmosis was found to be applicable in this treatment of these wastewaters, and other applications of the forward osmosis in wastewater treatment are shown in the table. In the write up on forward osmosis for sustainable water treatment, Shen et al. Noted that the method for freshwater recovery after forward osmosis is greatly dependent on the kind of draw solute used. Where monovalent ions such as sodium and chloride form part of this draw solution, reverse osmosis is mostly employed for the recovery, whereas multivalent ions, hydrophilic nanoparticles, micelles, and polyelectrolytes would require membranes with larger pore sizes like ultrafiltration and nanofiltration. The forward osmosis has several advantages. The process does not require external pressure, especially for niche applications of forward osmosis, which makes energy consumption lower compared to pressure driven processes. Fouling, reversal, and water cleaning is also easier due to the use of osmotic pressure for separation. Flexibility in choosing draw solution makes it easy to customize products either for freshwater recovery or for other purposes like pharmaceuticals and beverage production, in which case properties of products are maintained since no pressure or heat is applied. Furthermore, the regeneration and the reuse of draw solution is advantageous in saving cost. Challenging highly concentrated feed solution are better treated with forward osmosis. For example, for a highly saline feed, more energy would be required by the reverse osmosis to overcome the osmotic pressure, hence making the choice of forward osmosis a better one. With all these promising features of forward osmosis, it has some drawbacks that require attention. Apart from niche applications of draw solution, where the draw solute forms part of the final product, further separation is needed to recover fresh water. The low permeate flux due to the concentration polarization is another drawback for the forward osmosis. This concentration polarization affects the net osmotic pressure, hence reducing permeate flux. Again, energy requirements for the forward osmosis increases with the decreasing molecular weight cutoff. This is because the regeneration of the draw solutes would require membranes with smaller pores and more pressure like reverse osmosis. This, in effect, increases the overall energy requirements. Electrodialysis and electrodialysis reversal. Electrodialysis and electrodialysis reversal are processes that combine electricity and ion permeable membranes to separate dissolved ions from water. These processes make use of an electric potential to transfer the ions from a dilute solution to a concentrated solution through an ion permeable membrane. As shown in the figure, during the electrodialysis, two types of ion exchange membrane are used. One is permeable to anions and rejects cations, and the other is permeable to cations and rejects anions. There are also two streams of solutions, the concentrate and the diluate or the feed. When electric current is passed through the system, ions from the diluate migrate into the concentrate through oppositely charged membranes. The cations migrate to the cathodes, while anions migrate to the anodes. The cations are then retained by the positively charged ion exchange membrane. Likewise, the anions are retained by the cation exchange membrane. The outcome of this is a feed stream depleted of ions while the concentrate stream becomes rich in ions. The electrodialysis reversal involves the periodic reversal of the electrodes of the membrane and hence reversing the movement of ions. This causes concentrated streams to be diluted and diluted streams to be concentrated, hence reducing fouling of the membrane. The electrodialysis and electrodialysis reversal have been applied in many ways in wastewater treatment. The table shows some common applications. The electrodialysis and electrodialysis reversal are very useful in wastewater treatment mainly to remove total dissolved solids and other unionized constituent particles. They have a very high water recovery rate and require little pretreatment for feed water. There is also less membrane fouling due to process reversal, and the technology can be combined with renewable energy sources. However, the electrodialysis is not suitable for wastewater streams with high salinities because desalination energy is proportional to the ions that are removed. This would then be very expensive to operate. The process also does not remove non ionized compounds and substances such as viruses and bacteria, which are very harmful. This implies that a post treatment would be required, which would make the process expensive. Furthermore, due to the generation of chlorine gas at the anode, corrosion can set in. Pervaporation. This separation technique combines membrane permeation and evaporation to separate liquid mixtures based on a preference. As shown in the figure, the liquid mixture is fed to the membrane on the one side while the permeate evaporates on the other side. During this process, sorption of the permeate in the upstream occurs. By this, the more permeable component of the liquid mixture is absorbed onto the membrane, or the non-porous polymeric membrane, or the molecularly porous inorganic membrane. These components then diffuse through the membrane under the influence of a concentration gradient of the diffusing species and subsequently evaporate at the downstream phase of the membrane. The vapor is then condensed and recovered as liquid. This mode of mass transport across the membrane is known as the solution diffusion model. This technology has been applied mainly in ethanol water separation. It is, however, being explored for wastewater treatment in many areas of production. Edgar and others applied pervaporation in microirrigation of plants from wastewater. In the experiment, a dense hydrophilic pervaporation membrane was placed at vantage positions in the soil. Synthetic wastewater in a feed tank was circulated over the membranes where the permeate flux and enrichment of the wastewater were monitored. The results showed that this technology has prospects in the treatment of brackish groundwater or wastewater for microirrigation purposes. In a pilot scale experiment to remove organic solvents such as benzene, toluene, naphtha, butane, ethyl ether, etc., from dilute aqueous streams, Wishmans and others used 100 organophilic membranes to remove and concentrate these solvents from the aqueous stream. It was observed that it was possible to concentrate the organic solvents at least 50 to 100 fold, thereby making it available a cleaner stream of wastewater for reuse or discharge. In a similar work, Kondo and Sato used a polyether blockamide membrane, which is an aromatic hydrocarbon selective, to remove phenol from industrial wastewater discharged from a phenolic resin process. The wastewater contained up to 10% phenol and other contaminants. After experiments, the phenol concentrations detected were below 300 milligrams per liter. The characteristic nature of pervaporation makes it applicable for target specific contaminants. The table shows some target specific applications of pervaporation in wastewater treatment. Due to the specialty in application, for pervaporation membranes are specially designed to have higher affinity for the component to be separated. This implies that the chemical nature and structure of the membrane plays a significant role in achieving the intended separation. Other factors that affect the processes of pervaporation include the feed concentration, partial pressure, temperature, and feed flow rate. In addition to its ability to separate liquid mixtures, where conventional separation processes are limited, pervaporation is known to be an energy saving and eco friendly technology. There are, however, some drawbacks with this technology. Large industrial application is still not reached due to its highly sensitive operating conditions. Again, the application of pervaporation beyond dehydration is on the low side due to a lack of specialized membrane and the cost of these membranes. Now, let's talk about hybrid membrane processes. Hybrid membrane processes refer to the combination of one or more membrane techniques with other unit processes like coagulation, ion exchange, adsorption, or other membrane processes to give a better performance than either of the technologies as standalone process. Each component within the hybrid process tends to complement the drawbacks of the other, thereby enhancing the production of more quality treated water. With an increase in stringent discharge standards and the radical search for alternative sources of water, more hybrid membrane processes are being explored. Also, due to the high risk of fouling membranes, other unit processes such as coagulation, flocculation, sedimentation, and other membrane processes are introduced as pre-treatment steps to reduce fouling of the membranes. The main focus for hybrid membrane processes is to produce water for drinking or with different degrees of quality for other applications like irrigation, janitorial services, or to use as cooling water in industrial processes. In a series of applications, low pressure membrane processes such as microfiltration and ultrafiltration were combined with activated carbon in the treatment of contaminated groundwater drinking. The combination was able to remove particulate matter and protozoa, including Giardia, pathogenic bacteria, Cryptosporidium, and dissolved organic matter, making potable water available for use. In a similar fashion, Zhang Li and others combined coagulation as pretreatment to ultrafiltration, in which 10,000 cubic meter of potable water per day was produced from a highly turbid water in the Taihu River, China. The combination ably reduced fouling of the ultrafiltration membrane, leading to the maintenance of the specific flux of up to 190,000 and 200 liters per square meter or bar. The forward osmosis, reverse osmosis, hybrid systems. In other related developments, FORO hybrid systems are being explored for simultaneous treatment of wastewater and desalinations of seawater. The figure shows a simplified setup of an FORO setup for simultaneous wastewater treatment and seawater desalination. In this setup, wastewater of relatively low salinity is used to dilute seawater to reduce the pressure required by reverse osmosis for desalination. In this process, the chemical potential of the seawater provides a concentration gradient which causes diffusion of water from the wastewater stream through a semi permeable membrane into the seawater stream. As shown in the figure, the wastewater stream and the saline stream are circulated over the opposite sides of a semi permeable membrane or the designated FO. Through the contacts made with the membrane, water molecules move from the wastewater stream into the seawater stream, thereby diluting the seawater stream before the reverse osmosis step. The brine from the RO is recycled into the seawater feed tank to boost the concentration gradient. Consequently, the wastewater is treated simultaneously with the desalination of the seawater. This hybrid process has a huge advantage of low external energy requirements for solvent solute separation and serves as multi-barrier for contaminant removal. Membrane bioreactors. Another interesting hybrid membrane process worth talking about is membrane bioreactors. This is a technology that combines biological processes like activated sludge and membrane processes like ultrafiltration, nanofiltration, microfiltration, and others for wastewater treatment purposes or for resource recovery from wastewater. Over the past couple of decades, membrane bioreactors have surfaced as efficient water treatment techniques as they fill in the gaps left by conventional activated sludge processes, such as their inability to cope with fluctuations in effluent flow rates and composition, as well as their failure to meet higher effluent discharge limits for reuse purposes. The membrane bioreactors also save much space compared to conventional treatment systems. Two configurations are currently in use, namely side stream MBR and immersed MBR, as shown in the figure. The side stream MBR was the first to be introduced, With the side stream MBR, the membranes or filtration element are installed outside the bioreactor, needing an intermediate pumping system which transfers the biomass for filtration and residue from the filtration setup back to the reactor. This setup is advantageous in that the membrane module is easily accessible for cleaning. However, due to the high energy and pressure requirements, the side stream MBRs have had limited application in recent years. In the immersed or submerged MBR, the membranes are directly immersed in the tank containing the biological sludge, and the treated permeate is extracted as shown in the figure. This configuration was due this configuration was first introduced by Yamamoto and others, and it became highly patronized due to its simplicity and low energy requirements compared to the side stream MBR. It has, however, its own drawbacks in difficulty in cleaning the membrane units as the units are immersed in the bioreactor. Membrane distillation, or MD. It is a growing membrane technology being explored. This hybrid membrane process is said to have existed for more than 50 years with little development for large scale or commercial use. Membrane distillation can be defined as the application of heat to separate substances based on their volatilities. In this technique, water vapor is transported across the hydrophobic microporous membrane based on a vapor pressure gradient across the membrane. This heat driven process is mainly beneficial for separating feed solutions with high water content. MD is adapted to use low grade thermal energy, less than 100 degrees Celsius, to provide the needed vapor pressure difference between the feed side and the product side of the membrane. For example, Al-Qadiri and others applied MD in the treatment of produced water from the Arabian Gulf, where they found membrane distillation very promising in terms of achieving high permeate flux and energy utilization. Ki et al. Applied the membrane distillation in the treatment of table olive wastewater high in phenols. Membranes of different pore sizes were used to evaluate the effects on permeate quality and phenol concentration. In textile wastewater treatment, Calabro et al. Studied the energy efficiency of membrane distillation system with respect to distillate flux, distillate purity, and temperature polarization. According to their results, the energy efficiency of MD can be improved by increasing the driving force on the membrane. They found MD as a potential treatment method for textile effluent and the recovery of quality water for reuse. The table here shows some other applications of the membrane distillation in the treatment of wastewater. Characteristically, membranes for membrane distillation should have low resistance to mass transfer in order to enable free flow of mass. To enhance heat maintenance in the system, membrane material must have a low thermal conductivity, and very importantly, a membrane for membrane distillation must also have low affinity for water to guard against unnecessary wetting of the membrane. The pore sizes usually range from zero point 0.1 micrometer to 1 micrometer. Membrane distillation has many attractive prospects. It can be driven by renewable energy sources such as solar or wind. Waste heat recovered from industrial processes can be used. In terms of pressure requirements, MD uses low hydrostatic pressure compared to reverse osmosis. For example, MD can be performed at operating pressures near atmospheric pressure. Again, as compared to pressure driven membrane processes, membrane fouling is less due to larger pore size requirements. In terms of separating non volatile materials from volatile ones, feed product separation is 100%. Contaminant concentration has no influence on product quality. All this notwithstanding, MD has some drawbacks. Firstly, poor history of its usage leads to uncertain water production costs. Secondly, non-availability of membranes specifically designed for MD puts the process at very high risk when membranes meant for other processes are employed. This can lead to membrane wetting, which in turn creates room for organic deposits and consequently leading to vigorous pre-treatment requirements. This makes the process more expensive. And finally, since heat and mass transfer take place simultaneously, a fluid boundary layer is formed, which leads to temperature polarization. TP is a phenomenon that occurs as a result of difference in temperature between the bulk of the feed and the feed membrane interface, where evaporation of water occurs, and the difference in temperature between the permeate membrane interface, where the condensation occurs, and the permeate itself. This temperature polarization has a negative effect on the driving force, leading to lower permeate flux. In order to provide the needed driving force for membrane distillation, four main configurations are usually considered as shown in the figure. These are direct contact membrane distillation, air gap membrane distillation, vacuum membrane distillation, and sweeping gas membrane distillation. However, recent developments of membrane distillation have considered hybrid combinations such as thermostatic sweeping gas membrane distillation and liquid gap membrane distillation. Membrane fouling. Membrane fouling relies on different aspects of the setup, that is, membrane characteristics, operating conditions, and feed or biomass properties. Several of these variables combine in one form or another to intensify membrane fouling. Membrane modules. To achieve the required separation, industrial membrane plants require hundreds to thousands of square meters of membrane. There are many ways of economic membrane packages to provide huge surface area for effective and efficient separation. Usually, the designs of membrane modules are used for prevention of membrane fouling. Commonly used membrane modules are plate and frame modules, tubular modules, spiral wound modules, and hollow fiber modules. Future directions and challenges. Membrane technology is gradually revolutionizing water and wastewater treatment. Much work has been done in this area over the years. There is, however, still room for improvement in many areas. As fouling and high energy demand remain a major issue and non equilibrium pressure driven processes, continuous research is needed to find a lasting solution to them, either through introduction of rigorous but cheap pretreatment processes or through development of fouling resistant membranes. In membrane distillation, continuous studies are needed to adequately understand the concept of temperature polarization, and accordingly, developing suitable membranes will help make the process more viable for large scale application. Improvements in Drossel-Ute recovery processes are needed to make the forward osmosis applications cheaper. Future research should look at the possibility of other recovery methods for salt-based Drossel-Utes. Further studies in electrodialysis and electrodialysis reversal and pervaporation should focus more on membrane development and energy utilization. Conclusion. Overcoming the emerging global scarcity of water, energy, and other natural resources are grand challenges faced by humanity today. These critical resources are inextricably linked and therefore must be considered together as new technologies are developed. In essence, new effective methods to produce water at low energetic and environmental cost are essential. Membrane technology promises to provide a more efficient and economical separation solutions, which are then applicable at large scale for sustainable water and energy. The membrane technology is unique in its capability to separate smaller substances from a liquid, although it comes with some challenges. Hybrid membrane technologies demonstrate high potential for water and wastewater treatment. And finally, the key advantages of membrane performance lie in its advanced use of technology leading to less deposited foulant. Here are the references used in this presentation. Thank you for listening.